How's everybody doing? Everybody looks good. You know, it's beautifully sunny out there, just so everybody knows. Anyway, you wouldn't be able to tell from this room. But regardless, Santi and I are going to present, as you see here, computational design for prefabrication and modularization. One of the things that was mentioned just prior to us coming up here was that we were going to speak about Van Dusen, and I promise Van Dusen is a significant part of this presentation, but we also have another project called Orchard Commons that we're working on right now, which we'd love to show you as well. So just a little bit about us. I'll introduce myself, and then Santi can take over and introduce himself. Santi and I have worked together for some time now at Perkins & Will, and we both had an opportunity to work on the Van Dusen project together. But just so you kind of get some of the highlights here, I came originally from Winnipeg. I graduated at the University of Manitoba in 2007, and had an opportunity to come out to Vancouver to work with Perkins and Will, and I jumped at that chance, and it's been excellent thus far. I was the project architect on the Van Dusen Gardens project. Santi?
So I'm Santiago. I'm the senior computational designer at Perkins & Will Vancouver. I started in manufacturing about just over 10 years ago. I worked at Structurecraft Builders, which is also a local firm, for about 6.5 years, and then I joined Perkins & Will almost 2 years ago.
So I can see that the font is not the same. Anyway, that's okay. This is a common problem. So just to start out, we thought we'd give you a basic agenda of what we wanted to talk about today. As I mentioned, it's not all Van Dusen. We wanted to talk to you a bit about the Orchard Commons Student Residence Project. We'll then follow that up with more of a discussion about the computational design aspects that relate mostly to the facade. And then following that, we'll do an introduction, just a basic overview of the Van Dusen Botanical Garden Visitor Center project, followed by the target value computational design, which Santi will lead. So to go straight into the UBC Orchard Commons project, this is a great project for Perkins & Will. We started this project probably about a year ago or so. This is at UBC campus. The site is just that red dashed line there that you see. It's at the intersection, if you're familiar with UBC, of Agronomy Road and West Mall. And you see here just some of the basic design principles for the project that they really wanted to have an exceptional learning environment. So what this is a kind of a hub within UBC. It's, I think, the second of 3 that they're planning at UBC, and this is kind of a student hub. It's a learning environment, but it's primarily a residency for international students. So what UBC wants to do is market this as a kind of a sort of a mini hub, a mini campus, if you will, for international students to come to Vancouver and be tweened into the English language and be tweened into UBC campus. So this is something that is going to be marketed kind of internationally, and it's quite interesting from that respect. And of course, they want it to be a healthy community. They want to engage with food and nutrition as an important part of the project. They want to promote an active and healthy lifestyle, so there's some guiding principles for us there. They want to engage the surrounding community, so the building should feel at home within the context. Universal accessibility, of course, is a major factor. You're going to have people from all over the world coming to this hub, so you have to make it as accessible as possible. And opportunities to connect with nature. Nature is a very important part about what UBC stands for, and also create a sense of place. So they really wanted, of course, as they're marketing this to the international crowd, they really wanted it to be something that was identifiable, even architecturally. Just the basic program. I'm not going to go into the nitty-gritty of this. You probably can't really see it very well. But essentially, there are kind of 3 major components of the project. There's the Vantage College, which is actually the academic wing, the Commons block, which is where the dining and events are held, all the kind of commons facilities for the student housing, and then the student housing itself, which really makes up the bulk of the program. That's all the little green bits there. Those are representative of actually all the rooms. There are about 1,050 student residences. And I think the whole thing is about 40,000 square meters in area. So I love leading with things like this because, the architectural concept it was a series of explorations, let's put it that way. We spent a lot of time, and in fact, this is really, I'm calling from probably, 50 different types of program massings that we had come up with to look into the different ways in which people can occupy this site. So we looked at 3-tower schemes, we looked at 2-tower schemes, we looked at perimeter block, courtyard type designs, a whole bunch of different things, really to kind of find a way to create a unique living environment for the residences at an urban scale. But what we ended up with was basically a 2-tower scheme, and you can see the kind of basic partie in this diagram here. So we have essentially 2 towers for the residences with these kind of cascading student lounges that rise vertically on the edges of the building. We've got a long academic block that runs along Agronomy Road, and then all the shared programming for the student housing is that green mass that you see there connecting the 2 towers. So really we had a kind of, after doing all this sort of formal exploration of the massing, we ended up with something quite conventional in some ways. So we struggled to find a way to create uniqueness given kind of the massing that we ended up with. So we began to look at skin, and we started to explore different ways that we can create a new kind of aesthetic, if you will, based on the parameters that we could play with, which was really the kind of the skin of the towers. And we were looking at precast concrete, actually, because the client, UBC Properties Trust, had experience in using it in a previous project and thought that we could apply it on this project and kind of do it in a unique way. So we looked at a lot of different ways in which we could do it, a lot of random patterns, staggered patterns, all sorts of different arrangements, punched holes. We really thought, you know what, it's just not unique enough. So we kind of went back to the basics and thought a little bit more kind of conceptually, and I'm going to get a bit architectural here, I can't help it. But we were really thinking about kind of cultural identities. So you've got people coming from all over the world to Vancouver, and what is unique about those different cultures? Could we create a sort of diversity in the way in which we create the aesthetic of the building? And that has to do with kind of the international nature of the building. And what about nature? As I mentioned before, that kind of one of the original themes. What can we learn from kind of forms that you found in nature? So we were looking at some of the ripples in water and things like that. And we also had this idea that the social spaces that connected the building would be done in wood. So this is a major part of the kind of concept that we were working with in the project. And what can we learn from wood? So we started looking at some of the patterning that you might find in wood. And then, of course, truth in materials. So we want to use the materials in the building in the way in which we think they're meant to be used. So concrete, in fact, is actually more fluid. It's not necessarily designed to be a box. It could actually be quite flowing. So we start to think about that a bit. So again, we start to look at things like this. What about algae? We were looking at flowing forms, thinking about how there's diversity in forms like this, but they're actually quite simple. So the aspects of biomimicry, I think, is something that is prominent in the design. Things like this as well. So we're looking at parallel veins within a leaf. And we start to see these sort of patterns occurring in a lot of different ways. So for example, on the right, you see calligraphy. And this sort of felt appropriate because, of course, calligraphy is something that is seen in all sorts of languages. A lot of languages have calligraphy, and we called this the calligraphic effect, which you'll see in a bit. But really, I think the truth of the matter is that we wanted to create something like that you see on the left side, which is, having people come to this building, being able to look up at it and have a sense of wonder. How is this done? This is unique. This is a wonderfully new experience. So this is where we went, and this was sort of, I guess, the 21st century of a napkin sketch, maybe. That I drew this, almost a year ago or so, and like I said, when I drew it, there was no real kind of computation to this model, and you'll see basically the next steps as to how we start to add computational design to this basic overall form. And really to do that, we had to kind of identify what were kind of the essential components that we're trying to get to here. So we had a high thermal performance as one of the main objectives. And really what this meant was kind of a 60-40 split. So 60% of the building was to be solid and 40% of the building was to be glass. And this kind of comes out of the thermal performance objectives. And this is actually a bit rare in Vancouver to have this, but it's actually a lot more solid wall than you would typically have in towers that you'll see around Vancouver. And again, an iconic postcard view, but not to look like the project that they had done before, which is the Ponderosa. Unfortunately, I don't have any photographs of that project. And then, of course, what all architects want to do, I think, is do more with less. Create the biggest impact with the least amount of moves that you can. So we started with the basic straight line. And we wanted to, again, exploit this fluidity of concrete. So we took that line and we started to think about a single line with opposing forces. So different cultures are coming together and they're reacting against this line, creating this sort of curved spline. And we started to realize that in order to create the shapes that I was originally drawing was that, in fact, you can create those shapes by producing kind of a calligraphic effect. It's really taking that singular line and then creating that singular line again and shifting them vertically. And we thought this is a way to create diversity without adding any more complexity. And as I mentioned before, we were kind of given this task of using precast insulated panels. So how do we start to think about modularization, prefabrication? How does that affect the way in which we create these ribbons? Well, what we did was, in fact, we realized that, in fact, the ribbons are two parallel lines that are shifted vertically. So it's sort of what I'm getting at here is that there's a kind of a process of reduction in a way, because the original image that I kind of drew in Rhino or something and had a little fun with, I think what I wanted to do was this, but it actually took a few steps through computational design to determine what was the essence of the design moves that we were creating. So this is where we got to after that first exploration, and you'll see that it certainly looks a lot more subtle, I would say, than it did originally. But really, it's actually capturing, I think, in my mind, the essence of what we were trying to create. And I think one of the other fascinating bits of the computational design work was that we were able to sort of look at the subtleties of the facade. So here we see kind of a range of less to more in terms of the amplitude of the curves that we were creating. Less, of course, on the left and more towards the right. And we were able to dialogue with the design team about, where's the comfort zone? Where do we actually feel that we're creating the right effect? And we found kind of a sweet spot somewhere around number 2. All the while, all these examples are still showing that 60% solid, 40% glass. So that's a given. That doesn't change. So we're able to kind of manipulate the design of the facade while maintaining this constraint. So here I'm kind of showing the first kind of napkin sketch to kind of where we are. Well, we were there probably about 5 months ago. We've moved on a little bit since then. But Santi.
So there are 4 key points that I'd like to leave with you by the time we finish this portion of the UBC Orchard. The first one is that computational design is a medium to distill design intent, and I'll elaborate on that with the subsequent slides. The second point is that prefab in itself has some benefits. It brings some assurance or certainty in the construction process. Computational tools can amplify that effect by transcending it through design into construction. And there are a couple more points which I'll get to as we go through the slides. So what I'll do here is elaborate on the point of how computational tools can distill design intent. And in order to do that, I'll walk through part of the computational process almost on a step-by-step basis. But before that, I'll introduce the concept for those who may not be familiar yet with computational design. I like to describe it as a hybrid discipline, and it combines computer programming with design in one form or another. And it has emerged out of necessity because of very large and complex projects throughout the world. And there were no other way for to realize them if it weren't for devising new tools, new digital tools. And so there, sporadically throughout the world, there have been people who have moved away from their comfort zone, moved away from design, and have adopted some programming skills. And since then, there have been some new environments that allow designers to more comfortably program. So they're not in a fully immersive programming environment. They're in a hybrid environment that's partly design, part programming. So one of the most popular environments is called Grasshopper. It's a plugin for a software called Rhino 3D. And what we're seeing here is a snapshot of the visual algorithm for the UBC Orchard. And it is a depiction of how the logic of how the panels were realized. And there's about 10 steps that I'll go through. The first one is, how did we realize the calligraphy? The calligraphy, just to remind you, was a very important interpretation of some of the values that we wanted to embed in the design. So there's ideas of diversity, without conflict, and we wanted to put that in the first priority in the whole algorithm. We wanted it to be the first thing that would occur throughout this logical succession. And you can see there on the screen that there are a couple screen captures. The one above is what's being generated in the model in 3D. And the one immediately below it is the sketch that Harley made. And this is where we begin to distill, where we begin to extract the essence of the design. We're taking the idea and we're generating it explicitly by the principles that generated that sketch. So it's not just a spline. There's some thought process involved to generate that geometry. And that's what's being realized in that cluster of components. Each one of those boxes performs a logical operation. And when you combine them together through a certain flow, they'll result in geometry or other types of information. As we traverse through the logical algorithm, we'll find that the next thought, which is to offset and create a sense of calligraphy, is also depicted in a geometric fashion. And so the actual step-by-step process of how the concept was devised as in an abstract way is now being realized geometrically in a very methodic way, being as true as possible to the original thought process. And here what we're doing is we're taking each of these calligraphic ribbons and we're displacing them on one of the axes, on the z-axis, to create diversity from bay to bay throughout the facade of each of the towers. Then the next step is to truncate that, taking a snapshot of this geometry, and now we're truncated it within the scope of the actual facade, so for the 18 floors. And that's a perspective view, so you don't get a true dimension of the height of the geometry. It's just so that you could see the whole pattern in one shot. The next step is, well, now that we have a general geometry that we're generating, and we feel that there's a high fidelity of the design intent realized geometrically, now let's get closer and closer to the realization in the real world. So we know that we're going to work with prefab. How can we embed prefab principles inside the algorithm? And so that becomes the second priority. It's subservient to the architectural concepts. It's not the other way around. If it would have been that we would have started with the modularization, we may have been constrained with the architectural concept. So we wanted to explicitly define the architecture first, the modularization second. And here we bring in some project data such as the levels and split those curves into panelized shapes. The next step is to create a description of the different panel types. So for lack of a better term, panel typology. And there what we're doing is bringing in some information that will inform the designers on the distribution of the panels by using a set of colors, numbers to label the panels. This is common practice in computational work. Next is to get into further detail. These are insulated precast concrete panels, so there's an inner withe to the interior of the building, an outer withe, and then there's a layer of insulation in between. The inner withe is a rectangular shape, and it fits in between slabs. The outer withe is outside of the slab, so it has a more of a free-form shape, and it could extend a bit beyond. And so the inner withe is generated as you don't see it very clearly here, but there's a dashed line, a white dashed line, offset slightly within the profile of each of the panels. And this is the part of the algorithm where that gets realized. And we're going to pick up the pace a little bit here. And at this point, we have the different elements that we could use to realize the facade. We have the overall geometry, design intent, and we have the panelization. How can we explore different combinations? There are, I can't remember the number, there's 40 quintillion or so different unique combinations just in the position or the layout of the panels. So usually in optimization, the first step is to do a quick mathematical calculation. What is the total possible combinations? And that will inform you on what's the most appropriate computational strategy to explore through those different possibilities. And that informed us that we should use a category in optimization called stochastic optimization. So what that is that it reiterates, it makes a selection of random samples. It tests it towards a minima or maxima, and then based on that result, it'll change and have a new selection and repeat the process until it's gravitated towards the goal that it's been seeking. And that is the most appropriate solution for this variety of combinations. So we have various points where we could combine, where we could get different results with the panels. And before I get to that, what does it look like when you haven't optimized the facade? So this is a precedent project before my time in the firm, but you can see on the left-hand side, you have an elevation of the building. On the right-hand side, that's the variety of panels that were required for the curtain wall. That, at a glance, is an indication that there wasn't a proper optimization process in place for that project. What we have is a series of 18 panels that get repeated throughout the facade. The pattern is continuous and it gets offset vertically, so it is inherently, by design, optimized to be 18 panels. The next variant is what happens with the glazing in between, because if you shift the panels differently, you'll get different widths or designs for the windows. So how can we minimize that? This is where we begin to optimize computationally the pattern of the concrete panels, and we see whether we can reduce as much as possible the glazing units without losing the design intent, which is what's driving the whole algorithm from the beginning. So this is one combination, and we went through many of these different combinations. And one of the key points here is that we have the flexibility of exploring combinations without being preoccupied about what this will do with our overall process. And this is very important. This is probably one of the most important points that we could make in this presentation, is that as designers, we crave for flexibility, for freedom, to be able to make decisions, change our mind, ask questions, be inquisitive, interrogate different possibilities in design without having to be preoccupied with process. We want process to be instant. We want process to be so easy that you don't even have to think about the process. It just happens. And that way, it's as close to 100% creative as possible. And so as a computational designer and as an architect, we put a significant amount of effort into getting closer to that 100% situation. So going back to the screen, this is one combination, and you'll see there's the results geometrically. The geometry changes if you change some of the parameters that are generating the layout of the panels and the shape of them. And as we go through the different options, you get different results. If we change a combination of the geometry in another aspect, for instance, the detailing, and I'll show you in the next slide, we explored things like reveal lines or ridge lines. We want to test it back to some of these combinations without the expense of the exploration process. So we want to be able to say, well, we really like this idea of ridge lines, but not with the geometry we're looking at now. How about we go back to a geometry that we did a few weeks ago, We can easily do that with this because it's a relational algorithm. It basically executes every time you change something. So you have variables and you can save them, and you can just switch to another set of variables that you had saved and it'll just re-execute. And this is why this is commonly described as generative design. So this is a different pattern. This is obviously not what we ended up with, but you can see there that it could go the wrong way. You end up with these very slender glazing units in between the panels, and then the opposite happens in other locations. So then we look at further detail into the glazing, begin to replicate the glazing system in 3D, and you don't see it here, but we would bring in the concrete slab and see how that interfaced. So I should go back to the previous. And we also paid attention to reducing the variation with the precast inner wide sizes. So we actually grouped that into, I think, only 3 or 4 different types of inner wide, while there were 18 types of outer wides, and about 6 or 8 different window types, I think, except for the corner units. This is the example of expressing a bit more of the geometry with these stripes, which we looked at for some time. And then these are different options for what if we want the middle portion of the panels to be wider at certain points and narrower at other points. And so we described it as an innie and an outie. So it would be concave sometimes and convex sometimes. What if we want it to be always convex? What if we want it to be always concave? We can change these options and explore it with any of the other combinations of geometries that we needed to. So we have freedom to test one with another. If we made a decision to go back to the beginning of the algorithm and change something that was perhaps a new interpretation of our design intent, that would not destroy the work that happened afterwards. It's fluid and it's robust. We can also interrogate on what are the nuances of the geometry that we're looking at. The closest geometry or simple geometry that we can compare the sinuosity of our calligraphic curves was a sine curve. But we noticed as we tested different geometries for it to create that calligraphic expression that really, if we would have just went with a sine curve, it wouldn't have done it for us. It didn't have that something that created the expression that we needed for the calligraphic expression. It was a bit too, it lacked in some pronunciation of the curvature, and you can see the comparison between the two there. So we need to bring this into a BIM context because of many reasons that you are all familiar with. And on the left-hand side, you'll see in the algorithm that the Revit model was brought into the algorithm to reference. Up until now, what you've seen is a facade that didn't need the model or the project at all to be generated. But once we bring in the BIM project, we can take that and associate it with the building, and it'll just snap on to the different elevations of the towers. And so the left group is bringing in the information we needed from Revit. The right-hand side is to associate the algorithm onto the Revit model. And you can't see it here because it's too small, but the lower portion of that right-hand area, it has one component to send out information to Revit, and there's another component to send it to Autodesk Inventor. So in a few steps, there's the Revit model imported as dumb solids. The geometry gets associated, and then Community is a tool that I've been developing to interface with Revit. And there's one main distinction between this tool and other similar implementations of tools that have been done throughout the world. Mine has a series of geometric solvers, which allows the data that you output from the source program to be incredibly simple, and through geometry, elements get associated to one another within Revit. So you don't have to actually say this door belongs to this wall. You just generate the most basic geometry, and then the Community will know whether a door belongs to a wall and embed that family. So then this takes about 20 seconds to generate this Revit model, and I've also thrown in some of the floor plates for reference to make sure everything was aligned. So we come to a different paradigm of, usually we work in BIM from start to finish with the same file, and we modify continuously. And it's not like with AutoCAD. You used to be able to, with AutoCAD, create a file, but then if you wanted to do something a little bit different, you might do a copy, and you would create, version A, version B, B prime, whatnot, and you'd have a series of, you'd begin to pollute your hard drive with all these different little AutoCAD files that was becoming very difficult to manage. But at least it gave you the flexibility of just being able to create these throwaway files to explore, test ideas. Whereas with Revit, you don't see that necessarily happening because it doesn't necessarily intuitively go with the way in which the software was designed. There might be some that would argue against me. I don't know enough about that to be able to debate that. But here what we're looking at is when you can generate a BIM model instantaneously, then you can actually go back to a more of a simplistic process the way CAD was. You can't just generate a BIM model and it becomes a throwaway model, and then you can make a change and you can generate another BIM model, and you can keep them for keepsake, for comparing or for quick meetings and so forth. Then those are natural BIM elements, walls and windows that are generated from families that are already loaded on the projects. That's one of the thousands of lines of code showing the association between information from the computational file, in this case the width of a window, which is expressed as the length of a line that generates that window in the algorithm, directly to the width of the window in Revit. So there's a direct correlation. So moving it into Inventor, it's done in a bit of a different way, but it's similar principles. You're taking a very small subset of information, but you're generating a richness of information with the native capabilities of this other tool, which is Inventor. And so with Inventor, we could create a drawing that closely resembles a shop drawing, but it sheds clarity to the process. It helps that he or she that would actually be the one to do the work, to build this panel, to know exactly what's going on. We didn't get any questions when we set out to get some mock-ups prepared for us. We had no questions. They said we made their work fairly easy for them to get to this level. And it's showing all the information for those different 18 panels in the one drawing. The key here is that if we decided to go back and change the design intent or change the combinations, or change the geometry of the variables, we hit a few buttons and now we have a whole new drawing that it takes a little bit longer than what I'm making it appear to be, but it is incredibly faster than what it used to be before employing these kind of tools. So the key points here are the computational tools are a medium for distilling design intents. They actually allow you to extract the essence of a design direction. Computational tools reduce the uncertainty of rework by allowing designers to simultaneously explore or lock variables, thus providing more time for design. We can optimize prefab without compromising design intent. Prefab helps reduce uncertainty in design in and of itself. But in addition to that, computational tools allow this assurance to transcend design into construction.
Thanks, Santi. Okay, so we left ourselves with 11 minutes and 24, 23, 22 seconds to speak to Van Dusen, so bear with me. Van Dusen Garden Botanical Visitor Center was started in 2007, at the end of 2007. I think we were complete in 2011. Just some basic statistics here. The building was constructed by Ledcor. Construction budget was somewhere around $14.4 million. It's a 1,800 square meter visitor center. And when we first started this project, we thought a lot about its context, and the building is set in such a beautiful place. We were looking for inspiration that would drive the design of the project. And I'll tell you a really interesting story, for me anyway. when we first started thinking about the design, I was at home one night prior to a design meeting with Peter Busby and Cornelia Oberlander, and I was looking through my library of books at home, and I found this one book by Karl Blossfeld, who took these amazing photographs of plants, and the book is called The Alphabet of Plants, if you're interested. And I looked through this book and I found this great photograph, and I said, you know what, this is it. I've got to bring this image to this design meeting the next day and show it to everybody. Sure enough, Cornelia, the landscape architect, was doing the same thing at her home. So we both showed up at the meeting with this Alphabet of Book Plants or with this Alphabet of Plants book, and we looked at it and found this particular image together and thought, wow, you know, this is it. So there was some meaning to or fate perhaps behind the selection of this image. But in some ways, that although you'll see that the form of the building very much reflects the geometry that you see here within the orchid shoot, it had much more meaning than that. In fact, we saw that you know, a flower is rooted in its own place, harvests its own energy and water, is adapted to climate and site, is pollution-free, promotes health and well-being. It's an integrated system, and of course, it's beautiful. You know, when we were approached by Parks to do this project, they really had kind of two really main objectives. One was, you know, this building had to be the utmost in sustainability. They wanted it to really be the greenest building that we could possibly build. And they also wanted the building to be as visible as possible from Oak Street. So if you drive down Oak Street, prior to this building's construction, you probably wouldn't even really know that this garden existed. So that was kind of an identity issue for Van Dusen. So they wanted to create an identity. They wanted to create a building that would inspire a sense of wow and kind of, you know, draw people to the facility. So we wanted the building to be quite aggressive, quite loud in its language, but we also wanted to integrate it into the landscape. So we did a lot of studying before we actually created the design for the building. As I said, we wanted the building to integrate into the nature of the site, so we looked at the meadow system, the water system, and the forest system to learn how to create a building that could, in fact, be one with its surroundings. And here you can see kind of a site plan of the building in relationship to its neighbors. And you can tell just by the roof plan of this building. I don't know how many of you have been there before. How many have been to the Van Dusen Gardens? Oh, quite a few. Okay. Well, believe it or not, this is what it looks like from the roof, or from above, if you're a bird flying over or something. But, I mean, it really, in my mind, is quite amazing because it doesn't look like a building at all. And in fact, the land ramp that connects up to the roof plane is completely transitionless. So there's kind of a sense that the building is, in fact, tied in. And this is the plan of the building as well. You can see on the east side, on the Oak Street side, there are some large rammed earth walls that protect the inner sanctity, let's say, or they keep the noise away from the interior of the building. Where on the west side of the building, it's actually quite exposed, quite open to the landscape. In fact, from a geometrical perspective, it's quite interesting too. The center of the building is where the oculus is located. I'll show you in the subsequent slide. But the geometry of the walls and the roof, in fact, all radiate from the center point. The idea being that when you're at the facility exploring the gardens, the walls and the roofs are actually pulling you into the center of the building. On the left side, you see an image of the entry, and really this is sort of the roof that we were trying to create. Was a sort of a continuous, free-flowing sort of shape. And along the way, there was a lot of construction innovation for us and at Perkins & Will. And here you see kind of a sequence of some imagery, one being the kind of original Rhino file. This is a sort of free-flowing drawing, which was then cut into sections in Rhino to generate the various beams. There were, I think, over 100 or so unique glulam beams, 50 or so unique glulam fabricated panels, which were actually produced at StructureCraft shop. The glulam beams, I think, were from Structurelam, and again produced in StructureCraft into panels, which Santi helped out on quite a bit. And then once those panels were fabricated, oh, and by the way, actually, the panels themselves quite fascinating because they were really completely built in the shop. So the membrane was placed on them, the sprinkler piping, the electrical, the final ceiling finish, that was all included and built in the structure craft shop before it was moved to site. And some of these panels were about 10 feet wide by 60 feet long, or so, even some of them larger. And they were shipped by truck to site. The columns were already in place, and we watched one of the largest cranes I'd ever seen for a single-story building lift these ginormous panels and drop them on top of columns. I remember they were really fearful that the architects were going to be there and watching over everything. Just some of the early studies from Rhino. And here you see kind of the designing the layout of the columns prior to the panels being put in place. And some imagery of the fabrication that was occurring in that structure craft shop in Delta. Sort of a sneak peek from the underside. And one of the interesting things is when, we had almost this finished ceiling, like the roof was completely done, yet we haven't even poured slabs yet. Kind of fascinating on site to see this erection come together in this sequence. And at the center is what we were calling the oculus, which is sort of a major feature within the building for stack effects. So we modeled this quite extensively in 3D. So the thought was that as the sun kind of moves around the building, it would actually be turbocharged. The heat would actually be turbocharged by this heat sink that you see, that kind of yellow perforated surface, would I guess turbocharge the temperature differential between the lower areas of the building and the upper areas. And there's actually a sensor, heat sensor on the top of the oculus. So when it reaches a certain temperature differential, the vents open up on the top of the oculus, and vents open up lower in the building and draw air naturally up through the building. So what we thought was we'd create a real kind of design feature right at the center that speaks to this notion of sustainability. All right, Santi, you have 3 minutes and 6 seconds.
Okay, so I'll have to fast forward a little bit here. There's some background knowledge, but basically a lot of this work was prompted by the idea that risk or uncertainty in the design process stifles creativity. And so the impetus for using computational tools in this project was driven by risk mitigation. And so just to go through this really quickly. Okay. So there's part of the model, the structure, about 3,000 unique joists, 70 or so unique panels. It at first glance, it looked a bit difficult for it to build. So, but let's look closer at the geometry and some of the drawings that were available at the moment. What could go wrong with the roof? And so there are 3 things that we thought might deserve more attention. One of them was that the drainage of the roof didn't look like it was going to work. There were a couple major ponding points that were too far away from the demising walls. The cost of the glue laminated beams that were the sides of the panels, integrated panels, were having unrealistic curvature in terms of the lamination process for the glulam. And the third is that there was this concern that the smoothness or continuity of the ceiling might be interrupted because of the geometry that it currently had. And so, again, using some computational tools, we assessed these 3 risks. The key is that we did it simultaneously. So we could concurrently modify the shape of the roof, get instantaneous feedback about whether we're closer or farther away from these goals, and be able to negotiate these 3 values that we were trying to protect in the project within a week, a bit less than a week. And so they were pouring slab on grade around some areas where drainage pipes were being run in a few days after that. So it had to happen very fast, faster than the time I have left for this presentation. So here's a before and after. Here's a before and after of the ponding points example. There's an example graphically of the changing radii that was assessed in the roof. After that exercise, with another 2 weeks of work, we were able to add lots more detail. Otherwise, it would have taken a few months to get to this level. And this was very important because in a large room with various consultants and stakeholders, we could discuss issues, details throughout the project without having to wait for the information or the geometry to be available. We got there so much faster, and it led to, there's not even enough time for the key points, so thank you very much.